The cloud. Hopefully y'all enjoyed the day off. So if you didn't get the email, I posted 2 videos for you to watch. Well, actually it's 3, but one already covered what we covered in class. Now, why am I putting these over here? They go over here. So today we'll go over a couple of problems that were kind of covered in the video from your homework. And then if there's any other questions y'all have, just let me know. So the first one we're going to do is this one. So number 15. It says to qualify for a medical study, an applicant must have a systolic blood pressure in the 70% of the middle range. If the systolic blood pressure is normally distributed with a mean of 120 and a standard deviation of 3, find the upper and lower limits of blood pressure a person must have to qualify for the study. How in the world do you do that? First step is you need to notice what it's actually saying. So here you have the distribution of your random variable, which is systolic blood pressure. And it's approximately normally distributed. So it's something like that. And what does it say? You must be in the middle 70. That means that this negative Z naught to this positive Z naught, the area in the middle of those two is what? 0.7, 70%. Then you know the area in these 2 remaining tails is what? 1 minus 0.7. So in these 2 tails added together, you have 30%. And since the normal distribution is symmetric, that means that an equal amount of area is going to lie below this lower Z-score as above the upper Z-score. Then that means the area in this tail is equal to what? Half of 0.3, which is what? 0.15. Then, using this area, you can then find what? Then you have the probability of getting a Z-score less than or equal to this negative Z naught is equal to 0.15. Then you can look in the standard normal table to find the closest Z-score with this area to the left. Gosh dang it, sorry. There you go, that's what I did so far. So here it says you must be in the middle 70%. So that means the area between these 2 Z-scores right here is 0.7. So then the remaining area in the 2 tails is 0.3. And since the normal distribution is symmetric about the mean, then an equal amount of probability will lie to the left and the right of those corresponding Z-scores. Then you just have this equation right here, that the probability of getting a Z-score less than or equal to this is equal to the area to the left, which is 0.15. Now, I actually don't know what that Z-score is. 0.15. I think it's negative 1.04. You just look for a Z-score with the area to the left of 0.15. And if you look in the standard normal table, the closest you can get is 0.1492. So that's negative 1.04. So that implies that negative Z naught is equal to negative 1.04. That means now you have this z-score here. You're given what? It tells you that the mean mu is equal to 120. And the standard deviation is what? 3. Then you can find the data value x corresponding to this z-score by negative z naught is equal to, we'll say x naught. So this is the data value, so that's going to be the lower cutoff, minus the mean of whatever it is, 120, divided by sigma. Then you just plug in the numbers you know. So negative 1.04 goes here, 120 goes here, and 3 goes here. Then you just isolate this x naught here. And how do you do that? Multiply both sides by 3 first. So that would be minus 3.12 equals x naught minus 120. And then to isolate the x naught you want, you just add over 120. And that is 116.88. Is that what it said? So the lower blood pressure limit is that. Let's make sure that's all right. Where's that? Does it say it's 1 decimal place? Yeah, just 1 decimal place at the end. So this is 116.9. And that's actually the correct answer. Do you understand how I did that at all? Then, since this negative z naught is negative 1.04, then this positive z naught is what? Let's take the negative off. Then you can find the upper x boundary corresponding to this. So we'll call that x1. So then we would have, let's just 1.04 is equal to x1 minus 120 over 3. That's just using this equation here, but taking off the negative sign. Then again, you can multiply by 3 on both sides, and you get 3.12 equals x1 minus 120. And then add x1 over, and you get, or add 120 over, and you get 123.12. And it makes you round to 1 decimal place, so it'll be 123.1. And that's the upper limit. Negative 116 or positive. That'll be positive because you can't have negative blood pressure. And whenever you add over this 120, it turns that negative up into a positive. .04, this part right here. It said that the middle area between the two z-scores needed to be 0.7. So then I can find the area to the left and the right by just taking 1 minus it, because the total area under the curve should be 1, right? And then since this is the negative z-score of something, and this is the positive, an equal amount of area is going to lie to the left as to the right. Then that means that if I take this area here and divide it by 2, that's the area in each tail. Then I can find that area, which is this right here. And then I can find the z-score corresponding to that by using this. So all you do is look in the table for a z-score such that the probability of z being less than it is as close to 0.15 as you can get without going over. Sometimes your homework makes you go over, and I'll have to look at which ones it is. I don't know if it's this homework or the next one. Does that make sense how I did that? Okay. That was number 15. So I would suggest knowing how to do something like that. If you don't get the hint, you should probably get it by now. Now, the last section is probably the one that'll flip most people. The only thing that changes in this section compared to the other two is that the denominator gets divided by the square root of the sample size because you're dealing with the distribution of the sample means. Now, it says the average number of moves a person makes in his or her lifetime is 12 and the standard deviation is 3.6. What is it talking about? I have no idea. Oh, maybe moving. Let me erase this first, and I'll go over what it is. This one that we're fixing to talk about is number 20 on your homework. It says the average number of moves a person makes in his or her lifetime is 12. That means that mu of x bar is equal to 12. So for anyone who watched the videos, you know what this means. It means the average of the distribution of the sample means. Do I need to kind of explain what that is? So for instance, you have a population here. And from this population, you're going to draw some number of samples. And theoretically, you can do this an infinite number of times. And then from each of these samples, you can compute the sample means x bar from each of them. And what this says is whenever I take the average of all of these sample means, it should actually equal the population mean. So in the video, I say that whenever you have a variable x that is normally distributed with a mean mu and a standard deviation of sigma, then the distribution of the sample means x bar is distributed normal with that same mean mu, but the standard deviation changes to sigma over the square root of n. Would you like to know why that is? Okay, this is going to get real mathy real quick. So the variance of x bar is equal to the variance and x bar. Remember, you can write x bar is the sum of the data values divided by the sample size, right? Then replace that definition here. So the variance is the sum of the xi's over n. Now there's this weird fact that says if you have the variance of ax, it becomes a squared the variance of x. Then you're going to use that fact here. So then this becomes, this n doesn't have to do anything with the summation. So I can break the n outside and square it. So it becomes 1 over n squared times, and these xi's, they all have the same variance because it's from the same sample. And it becomes the sum of the variances of the xi's. And how many xi's do you have? That just means how many data values are there? N. Then this becomes, where the heck's the eraser? There it is. Then we have 1 over n squared. So there's n number of data values, right? So then it would be n times the variance of each data value, because it's the same. And the variance is sigma. So then you cancel out one of the n's, and you're left with sigma over n is the variance of x bar. So then if you take the square root, that implies that the standard deviation of x bar is equal to sigma over the square root of n. That's something probably from a 3000 level class. What's up? No, you don't. Someone just asked why it was, so I just showed you why. There you go. You just need to know how to use the z-score formula. Then let's go back to the problem. Did that get real mathy real quick? Yep, if you don't know that rule, you can't do it. That's why I don't introduce it. Let's go back to this. So it says the average number of moves a person makes in his or her lifetime is 12, and the standard deviation is 3.6. So we're given that the mean, I don't really need this here. The mean is equal to 12, and the standard deviation is equal to whatever it says, 3.6. Now let's see what it says next. Answer the sample. Oh, assume the sample is taken from a large population and the correction factor can be ignored. Don't worry about that. Round the final answers to 4 decimal places and their intermediate z-value calculations to 2 decimal places. It says find the probability that the mean of a sample of 25 is less than 10. That means it's asking for what's the probability of X bar being less than 10. Then you can find the z-score corresponding to this by using this right here. So the same idea applies as from section 6.2. You have z is equal to the data value of interest, which you're looking at. In this case is a sample mean of 10, minus the overall mean, which was 12, and then divided by the corresponding standard deviation. But the standard deviation for the sample means is sigma over the square root of n. So this would be 33.6 divided by the sample size square rooted, which says 25 is the sample size. So that is what it would be. And that would be the z-score. Then plugging that in the calculator, you get, let's see, 10 minus 12, 3.6 divided by square root of 25. Negative 2.78. Then that means that the probability of getting a sample mean less than 10 is the same as the probability of getting a z-score less than this one, negative 2.78. And how can you find this area? You look at it in the standard normal table, so you just look for negative 2.78. And the area to the left of that is 0.0027. That's the answer to the first part. Y'all see how I did that, or where I found it? Then, so you're saying that the probability of getting a sample mean less than 10 is the same as the probability of getting a z-score less than negative 2.78. So if you draw it out pictorially, here's negative 2.78. You're interested in the area to the left of that. Then you can find the area to the left of this by just looking up this z-score in the table, and it will tell you the area to the left of it. So it should be what line down? 1, 2, 3, 4. Oh, it's too many down. Just go to negative 2.7 on the left where it says z, and then intersect that with 0.08 at the top, and you should get 0.0027. And is that correct? It is. The next part says find the probability that the mean of the sample is greater than 10. What is relation of B to part A? In this case, it wants you to find, so this is A. Yeah, they're complements. So the probability of X bar being greater than 10. And remember, does it matter if I put that there or not? The answer is no. Remember that the probability for a continuous random variable, the probability of any single outcome is 0. That means it doesn't matter if I put this less than, greater than or equal to, or just greater than there. It won't change the probability. Then someone just said it was the complement. So then what can you do? So this is just equal to 1 minus the probability of X bar being less than 10. And you computed this probability right here. So it's just 1 minus 0.0027, which is 0.9973. Did I put that on an exam? I think I put that on an exam a couple semesters ago because I remember those two numbers. If I put one of these on the exam, please know how to determine whether you're looking at the probability of X bar being less than something or X being greater than something. So you should be able to determine, if I say find the probability of the mean being less than or equal to something, then you have to deal with this right here. If I just say find the probability of some value being less than or equal to something, we're just talking the distribution of X, not the distribution of the mean. If you look at the spring 2021 exam on Canvas, where is it? I put it up. Here it is. People online, I'm not going to show you because you can just look it up. But if you look there, this first question here deals with it. Or number 2. How many people do you think got this right out of a class of 70 something? Maybe like 10. So that's how you need to determine how and where to use it. So it says find the probability that the mean of their age is less than 8. So I tell you find the probability of X bar being less than or equal to 8. So I indicated what you needed to find, but they used the wrong z-score formula, which will give you a different answer. But I was nice and gave them partial credit for it because lots of people did it. So if you didn't get the hint from the first exam, look at the 2 exams I posted on Canvas. If you can do those 2 and do well on both of those, you'll be fine for the exam. Now let's look at the last one. Find the probability that the mean of the sample of 25 is between 11 and 12. That means for C, we're looking for the probability of X bar being between 11 and 12. If we draw it out pictorially, let's look at this. Dang it, I have to erase that. So here we have the distribution of X bar. And say here is a sample mean of 11 and here is 12. We're interested in what area, the left, the middle, or the right. We want the probability of it falling between, so it's going to be in the middle. And how do we find the area between 2 values? You're going to convert this to a z-score, look at the probability of z being less than that, then subtract off the probability of z being less than this. Then the first thing you need to do is convert these 2 to z-scores. So let's call them z1 and z2. Then z1 is equal to the sample mean of interest, 12, minus the actual mean, which was 12, and then divided by 3.6, divided by the square root of 25. And what should you get? This is using one of the facts Yeah, it's 0 because this mean is actually the mean. The sample mean is actually the overall mean. So this is 0. Now, then what do you think the probability of z being less than or equal to z1 is equal to? So just the probability of getting a z-score less than or equal to 0. Remember, the distribution is symmetric about 0, right? So the probability on each side should be half of the total probability, which is 1. So therefore, the probability is 0.5000. And if you look actually on the standard normal table, 0. Where's it at? 0, 0 is 0.5000. Now look at the z-score corresponding to 11. Z2 is equal to 11, the sample mean of interest minus the overall mean of 12, divided by sigma over the square root of n, so 3.6 divided by the square root of 25. If you plug that in, what do you get? 11. Yep, negative 1.39. So just round it to 2, so it's negative 1.39. Then you can find the area to the left of this z-score. The probability of z being less than or equal to z2. If you just look in the table, look at the probability of z being less than negative 1.39, and you get 0.0823. Oops, that was ugly. Then to find the area in the middle of these two, I just take the probability of it being less than the upper minus the probability of it being less than the lower. And if I do that, the area in the middle is, what is that? 0.4177. Let me see. And that is correct. So does everyone see the connection between section 6.2 and 6.3? The ideas are still the same. It's just the only thing that changes is the standard deviation. And the fact that you're dealing with the distribution of the sample means instead of just the distribution of your random variable x. Everyone okay with that? Now the last one we'll go over is the final one on your homework, which is number 21. This one may be a little bit tricky. It says the standard deviation of a random variable is 17. If a sample of 80 is selected, I'll just write it up here. This one doesn't have to do anything with using this z-score formula. It just has something to do with the standard error. It says the standard deviation of a variable is 17 and the sample size is 80. So that just means sigma is equal to, what does it say? Did I just say 7 or 17? 17 and n is equal to 80. Part A says find the standard error. Find the standard error of the mean. That just means find sigma of x bar. And we said that the standard deviation of the distribution of the sample means was sigma over the square root of n. So that's 17 divided by 80, which is, how many decimal places does it say in a round to? 3.213. That's how you do the first part. Next part. Find the sample size that cuts the original standard error I'm just going to say standard deviation in half. Then what do you have to do here? All you have to do is look for what is n in this case. So it's telling you want to cut this standard error in half. So take half of that. That would be 0.213 divided by 2. 0.1065. So it's saying I want this to be equal to sigma, which is 17, divided by the square root of the sample size. Multiply by the square root of n on both sides, and that gives you 0.1065 times the square root of n is equal to 17. Divide this over. You have 17 divided by 0.1065 is equal to 159. So this implies the square root of n is equal to 159.624. Now, how do you get rid of the square root? Square both sides. So if you square that, holy cow, is that right? That is huge. What did I do wrong? Oh. Thank you. 1.901. Thank you. So then that, and then to take half of that would be 1. That is massive. Thank you, Grace, divided by 2.9505. And then you do the same thing. Multiply by the square root of n on both sides. You get 0.9505 is equal to 17 times the square root of n is equal to that. Divide that over there. Crap. Is equal to, says the square root of n is equal to 17.885. Then if you square that, it gives you 319.88. And you can't sample 0.88 of a person, so then you round that up. So you need to sample 320 people. And that's the correct answer. Everyone okay with that? Okay, cool. We'll take a quick 10-minute break real quick. I gotta run somewhere. All right, I guess we can start back up. So if you haven't watched those videos, please do. They're not too long. I think if you add the 2 times together of 6.2 and 6.3, it's about the length of one class. I did record them very late at night, so I may sound tired, sorry. Now we're on to the last section, which will be covered on the exam. I don't know how far we'll get into it. The last chapter that will be covered on the exam. I will try to finish 7.1, and we may touch 7.2. We probably will not touch 7.3. Oh, also, if you didn't watch the video, there's one section in 6.3 that I cut out because we didn't need to do it. And it's on your homework, so. Now, chapter 7 is all about what is called confidence intervals. So if you see me write C dot I dot, that's what stands for confidence interval. That's just the shorthand I use. Now, let's begin. Introduction. So a very important aspect of inferential statistics is using information obtained from a sample to estimate parameters of a population. So how we take sample data and then we try to infer a certain value that the population will take on based on that sample. However, we must ask ourselves, how good of an estimate are we making when we actually take just a sample? Because as we learned in chapter 6, there is something called sampling error. It's the difference between your sample and the actual population. Then, the first thing, a point estimate is a specific numerical value estimate of a population parameter. So a point estimate is an estimate for a population parameter. And obviously this estimate is not going to be exact, so we need to create some error around it such that to a certain degree of confidence, we can say that we are such confident that the actual population value will lie in that interval. Then you'll probably need to know this. It says the first example, the best point estimate of the population mean is, what do you think? Is the sample mean. X bar. In particular, it has this property that if I take the expected value of X bar, so that's what I was talking about earlier. If I take an infinite number of samples and I compute the average for each of those samples, and I get some sample mean, and then I take the average of all those sample means, I will indeed get the population mean mu. So when this happens, when the expected value of something is actually equal to the population parameter, we call this an unbiased, that's how you spell unbiased. Some books also use consistent estimate or estimator. That's not in your notes, but you may need to know it. Have I lost anyone yet? Cool. Now, if we wish to estimate the average age of all OSU students attending OU, we could take a sample of, say, 100 students and calculate the average age. So let's look at this as an example. Say the average age of 100 students is 21 years old. That just means we're saying the average from our sample, X bar, 21. Then we can estimate the average age for all OSU students to be at 21 years. That's just saying we have this sample mean is our best estimate for the population mean, so we're going to say it's equal to that. So in that case, it says has two little dots, or I don't know if it has two little dots or not, but what I put was mu is the population parameter to estimate. We'll just say mu is the parameter to estimate. And why is it mu? Because we're dealing with the population age of all OSU students, right? So age, we're just going to take the average of all of them and look at that. So we're looking at mu. And the second one, or second bullet point, X bar equals 21 is the point estimate for mu. So based on sample data, I can compute some point estimate. In this case, the point estimate for the population mean mu is actually X bar. So if I put a question on the exam, the way I structure it, the first part is what is the point estimate? So you'll need to know whether you're looking at a confidence interval for the population mean or for the population, what is it, proportion, that other one. So we won't cover the proportion probably on this exam, but whenever we have a proportion, we're going to know that the population proportion is P and the sample is P hat. And in that case, P hat is the point estimate of P. But you don't really know that. So it's saying we basically don't know how accurate that estimate is actually going to be because it's sample data. So it's going to differ from the population in some way. Then we have to create what is called a confidence interval. To a certain degree of confidence, we can say that the population parameter, so the average age of all OSU students, will lie in some interval. I don't know how accurate this is. It says example, and then I write out one. So this probably actually isn't that accurate, if we're being honest. So say, for instance, my margin of error so this will be the form of a confidence interval. The point estimate plus or minus its margin of error. And how we find the margin of error, we'll talk about in just a little bit. So we had our point estimate, which was the sample mean was 21. And let's just say the margin of error is 0.7. Then we create a confidence interval from that. The lower limit will be found by taking the point estimate minus the margin of error. So if we do that, it's 21 minus 0.7, so 20.3. And then if we want to get the upper limit, we add it, so 21 plus 0.07, so 21.7. And we'd say this is the confidence interval in that case with this margin of error. Now, these intervals right here are called confidence intervals. And that is all for the first page. The next one. So a confidence interval is a specific interval estimate of a population parameter determined by using sample data. We talked about that. We take a sample, we get a point estimate, and then we use that point estimate and the margin of error to calculate the confidence interval. So what is the confidence level? So we need to give a definition for it. You may want to know this definition. So I'm just going to shorthand it by conf level. So the confidence level is the probability. So prob, short for probability, that the interval will contain the parameter assuming a large number of samples are selected. So that is the definition for the confidence level. Then interpreting the next part. So what does a 95% confidence interval suggest? We're 95% confident that the population parameter will lie in that interval. That's basically what it says. How I wrote it is we are 95% confident the confidence interval, so just the CI, will contain our parameter now. In this case, in this class, we're going to talk about the two parameters are going to be mu, the population mean, and p, the population proportion. You can also create confidence intervals for the population variance and the population standard deviation, but we will not do that. It involves something called the chi-squared distribution, and we won't cover that here. We used to, but we don't anymore. Now, that's it for the introduction. So actually, let's get into what is the confidence interval and how do we compute it. So we're going to talk about, in this first section, confidence intervals for the population mean mu when we actually know sigma. Then 7.1. When sigma is known. Recall earlier that I said the general form of a confidence interval was the point estimate plus or minus the margin of error. So we know how we're going to find the point estimate. We talked about it. For a population mean, the point estimate will be X bar. Now, how are we going to find the margin of error? So we're going to write it as plus or minus some critical value. So we'll call that CV times the standard error of the estimate. So that would be the standard error of X bar. And then we know one part of this. What's the standard error of X bar from chapter 6? That was just the standard deviation of the sample distribution of the sample means. That's sigma over the square root of n. And if we know sigma, then the critical value we're going to use is a critical Z value with area to the left of alpha over 2. So we were able to find these last section. We looked at some particular area to the left and we wanted to find a corresponding Z score. So the idea here is going to be the same. It's just the notation slightly changed. Now, let's point out the key parts of this confidence interval that I think you should know, and you should know how to identify them. This first part, X bar, is the point estimate. This sigma over the square root of n is the standard error. This Z alpha over 2 is the critical value. And finally, if I multiply this critical value by the standard error, this part right here is the margin of error. So just like I said before, we have a point estimate plus or minus the margin of error. In this case, the point estimate is X bar and the margin of error is given by Z alpha over 2 times sigma over the square root of n. In a second, we'll talk about how to actually find these critical values. It's just like we did in chapter 6. Now, a little note that I put down at the bottom. You should probably know this. the margin of error is the maximum distance between the point estimate and the parameter. You may need to know that definition. Now, let's look at this thing right here on the next page. Now, let's draw something out. So what does this look like? So here you have the distribution of the sample means X bar, and it's approximately normally distributed, so it has a bell shape. Here we have some lower limit of the confidence interval. And here we have some upper limit of the confidence interval. We'll say, why did I say CL? It should be a UL. And the area in between is 1 minus alpha. And this will be what our confidence level is. So if the area in between here is 1 minus alpha, then the area in each of these is going to be alpha over 2. Then if we have some parameter, in this case, we're going to look at mu, is at the center of the distribution. Then this distance out here to the lower limit and at the upper limit is the margin of error. So this is Z alpha over 2 times sigma over the square root of n. And similarly on this side. Then, based on the level of alpha, I can find the area to the left of some unknown z-score. Then I can find that z-score in the table to actually use that in my confidence interval, because I will know the sample mean X bar, and I will know the sample size. And also sigma is known in this case since we assumed it, so you can compute the confidence interval. Then it says, if we wish to calculate the confidence interval in this part, some assumptions must be made. So obviously, the population standard deviation sigma must be known, or you can't use a critical z value. The sample must be random, and the population is normally distributed, or the sample size is greater than 30. Why is it that last part, the sample size is greater than or equal to 30? For someone who watched the video, what was the last video that was section 6.3? Yeah, central limit theorem. You can say that the distribution of the sample means that the sample size is large enough is approximately normal. So that's where that comes into play. So then that would allow you to use the critical z values. Now, how do you actually calculate one of these critical values? So we'll talk about that right now. Say we want to be 95% certain that the true parameter falls within our confidence interval. Then we need to create a critical value that gives us 95% certainty. It's saying we want a confidence level of 95%. Now, this is the general form. So the confidence level is equal to 100 times 1 minus alpha percent. You will need to know that. Then I'm given the confidence level here that I want it to be. So all I need to do is solve for alpha in this case. If I do that, this will be 95% equals 100. We'll just write percent here, times 1 minus alpha. Divide the 100% over, and the percents cancel out, and that leaves you with 0.95 equals 1 minus alpha. And what does that imply alpha is? If you want to add alpha over and then subtract 0.95, you'll get that alpha is 0.05. The easiest way to determine is move the decimal over 2 places on the confidence level, take 1 minus that, and that will tell you the value of alpha. If you would have looked here, move it over 2 places, that's 0.95. 1 minus 0.95 is indeed 0.05. Then, based on this right here, I should have alpha over 2 area in both of these tails here. Then what is the area in just this one tail here? 0.05 over 2, which is 0.025. Then, where in the world did that go? There it is. Now I want to look at the area to the left of this, and that is alpha over 2. And then I can find this corresponding negative z alpha over 2. I guess I can write this here. So the probability of z being less than or equal to negative z alpha over 2 is equal to alpha over 2. The probability of z being less than or equal to the positive z alpha over 2, which will be this one over here, is, what do you think? 1 minus alpha over 2. Because the area to the left of this is alpha over 2. The area to the right of this is alpha over 2. And the area to the left of that is 1 minus that. Then you just need to look in the standard normal table to find a z-score such that this happens, such that the probability of z being less than or equal to this negative z alpha over 2 is equal to alpha over 2, which is 0.025. Someone look in the table and tell me what that corresponding z-score is. I'm pretty sure it's exactly in there. Yes, it is. Anyone? I'm making y'all do it, so I don't need to know how to do it. It's just like we did in the last section. You look for in the middle of 0.025, and then you intersect the 2 digits. If you do that, you get what? Yeah, correct. Negative 1.96. This implies that minus z alpha over 2 is 1.96. So what does that imply about the positive z alpha over 2? That implies that the positive z alpha over 2 is just take the negative off, 1.96. Now, how would I get this positive one here? You could either just take the negative off, or you could look at this one right here. The probability of z being less than or equal to the positive z alpha over 2 is equal to 1 minus alpha over 2. So that would be 1 minus 0.025, which is 0.975. And if you look at 1.96, the area to the left, it is actually 0.975. And that's the way you could have found the upper limit. Does that make sense? How I did that? Now let's look at the next one. It says, what is Z alpha over 2 for 99% confidence? So in this case, it would be 99% is equal to the confidence level formula. And if you solve for alpha, what do you get? Yeah, 0.01. Then just looking here, doing the same idea, the area to the left of this negative z-score, or the negative critical value here, is going to be alpha over 2, or 0.01 over 2, which is 0.005. Then look for a z-score in the table with this. With this is equal to 0.005. And tell me, what do you get? Oops. I'm pretty sure this one isn't exactly on there. Where the heck is it? There it is. The closest without going over 0.005 is what? 0.0049, which is at negative 2.58. This implies that the negative z alpha over 2 is negative 2.58. So that implies the positive is just take the negative off and it's 2.58. The last one on here, I will leave to y'all. All you're going to have to do is find alpha. And then you can use alpha over 2 area to the left of this to find the corresponding z-score. And you should get negative 1.65. First, I'm going to go over this example real quick since we have 4 minutes left. I'm doing this so you can get started on your homework if you want. The example says a university wishes to estimate the mean GPA of its undergraduate students. A staff member randomly selects 45 undergraduates and calculates their mean GPA as 2.56. In that case, that means X bar is 2.56. So that's just the mean GPA for our sample. And the sample size is what? The number of students we selected, which was 45. And then it also says if the population standard deviation is assumed to be 0.52. So that means sigma is 0.52. Calculate a 98% confidence interval for the mean GPA of all undergraduate students. So we didn't actually figure out what the corresponding Z alpha over 2 for 98% confidence would be. But the idea is how to find it is still the same. The area to the left of some negative z-score is going to be 1. It'll be alpha over 2. So in this case, our alpha, if we have 98% confidence, so 98% the confidence level implies that alpha is what? Move the decimal over 2 places to the left and take 1 minus it, you get 0.02. So alpha is 0.02. Then take alpha over 2. That would be 0.01. The area to the left of some unknown z-score is going to be 0.01. Then look in the table to find that that unknown z-score actually is. So the negative one is 2.33, negative 2.33. So the positive one is 2.33. The way I usually have it is step 1 is the point estimate. Step 2 is the standard error. And wait, I can't remember if that's critical value. The critical value, step 3 is the standard error. Step 4 is the margin of error. And step 5 is give the confidence interval. The point estimate we already found is the sample mean, X bar is 2.56. The critical value we just found was 2.33. The standard error we can find by taking sigma over the square root of n. So 0.52 divided by the square root of 45. And if you do that, and I didn't even simplify that, I just left it as that. Then you can find the margin of error by taking the critical value and multiplying it by the standard error. So this is z alpha over 2 times sigma over the square root of n. So that would be 2.33 times 0.52 over the square root of 45. And then you use the idea, you have the point estimate plus or minus the margin of error. So that would be x bar plus or minus the margin of error. If you do that, x bar was 2.56 plus or minus 2.33 times 0.52 over the square root of 45. If you work that out, you get 2.38 to 2.74. So if you need to, I'll go through that again at the beginning of next class. But that's how you do it in general.